All right, go over a couple more of these systems of nonlinear equations with you, okay? So, just picked up a couple examples just to explain, okay? So here, our graphs are, as you can see, the natural log of x, which follows this red curve. Hopefully you would remember that, okay? And the natural log of 2 minus x, which is a translation. And how I determined that translation was quite simple because I know that natural log of a is only defined for arguments. That's what you're taking the natural log of, which are positive. So mandating that 2 minus x is greater than 0, which says, of course, negative x is greater than negative 2, or x is less than 2, which means I have my asymptote here, okay, and I have my curve sweeping in the other direction, which at most is going to intersect at one point here, okay? And my guess is that, that point is going to be the x value of 1. And in fact, it is, as we'll show you. So to solve these as a system, I just simply set them both equal. And of course, then you have to remember how to deal with logarithmic equations. We raised both as powers of e. Then we took advantage of our cancellation, another property of exponents, which just gives back the argument x equals 2 minus x, which effectively says 2x equals 2 or x equals 1. So yeah, the point of intersection there is 1 comma 0. Okay? And again, this is a review of graphs, so if you're a little tenuous about how we got those graphs, then you have to go back and review those logarithmic functions. Okay? Here we have the graph of a line, 2y minus 3x equals 6, and the graph of an ellipse, okay? Of course, I graphed each of those. The line is easily graphed by finding its intercepts at when x equals 0, of course, y equals 3. When y equals 0, x equals negative 2. So I graphed those 2 points. And I graphed my ellipse having similar um, intersections, okay, but then having those points which are symmetric. And lo and behold, those are the 2 points of intersections. And any other line would only intersect an ellipse at most 2 points. It could be tangent somewhere, but it could go through nowhere, intersect nowhere. It could have one intersection or at most two. We've already accounted for those two right there because both are points on the ellipse. Okay, now if you wanted to, I guess you could do a systems of equations. Okay, so if you redefine the line, slope-intercept point, 3/2 x minus 3, plug that in, do a little algebra, I'm sure that you should be able to come up with those. In fact, I would ask that you do that. Those values of you know, the x values mainly of 0 and negative 2, which of course would then give you those the corresponding y values. Okay, so I would suggest you do that. Another one we're looking at is what is the point of sine of x and the cosecant of x? Well, of course, the cosecant of x is the reciprocal of the sine of x, and so again, just looking at the graph, sine of x and then the cosecant of x, they touch at their high points right there and low points. So when the y value is 1, they touch, which of course occurs first at pi over 2 and then subsequently twice per cycle. So um, solving these, I said sine of x equals cosecant of x. Of course, cosecant of x is 1 over sine x. Cross multiplying gives me sine squared. So then I get, either the sine of x needs to be both plus or minus 1, which of course first occurs at pi over 2, and then 3 pi over 2, and then all cycles down the line. So that's just a couple more of our nonlinear systems, okay? And most of these were solved basically with our with most completely with our knowledge of the graphs, okay? Analytically, yes, okay? But the graphs are going to, your skills with your graphing are going to be more, uh, prove more vital for finding these points of intersection, and that's, lo and behold, what the purpose of this exercise is. Okay, so there's a few more for you.